Hello and welcome to a new video. Today we're going to talk about random number generators, selective activation checkpointing, and CUDA graphs. So as a quick refresher, let's talk about activation checkpointing. So imagine we have a function that's torch.sigmoid, torch.rand like x, my, smx. The critical thing I want you to notice here is that this is a random call. And so if you invoke it twice, you'll get different tensors, right? Now, what is activation checkpointing? Activation checkpointing is when we invoke a function in the forwards, typically we'll get an activation that we will save in memory, such that when we run our backwards, we can use this saved activation as part of our backwards backpropagation calculations. Now, what checkpointing does is it says, do not save this activation. And instead, when we come backward, when we do our backwards, we're just going to recompute this activation by rerunning this function. Now you can see that this is problematic when you have randomness, because when you compute this first activation, you'll calculate one tensor, and then when you do the backwards and you do this recomputation, it's actually not a recomputation because this rand-like generates a different tensor. So the challenge in CUDA graphs and the compiler is we want to make sure that when we're doing this recomputation, we generate the exact same tensor that we generated in the forwards. Now, from an API perspective, how do we do this? So the basic idea is that there's this API called get RNG state that gives us a state of the random number generated at a particular time. And if in our forwards, we save this state right before we call our random call, our random ops, then if we pass the state back into the backwards, and then we initialize the state before doing our recomputation, then this torch.randperm will be the exact same as this .torch.randperm. And this is basically what we do. And then afterwards, we do this cleanup where we kind of reset the RNG state before we injected our RNG state. Okay. And then the last thing I want to talk about is how this PR actually does it. This PR does it in AOT autograd. And so as you can see in the dynamo graphs, there's actually no RNG states inserted. But in the AOT autograd graphs, it will actually insert one RNG state for every recomputation operation that has randomness. And at runtime, what we do is Dynamo will gather the user inputs, invoke the AOT callable, and the AOT callable, before it actually invokes, the kernels and stuff, will actually inject some CUDA RNG states to fill up these inputs. Okay, so now let's look at how the actual code works. So the magic happens within torch.partitioners, and basically for every single recomputation RNG operation, we're going to call this apply graph safe RNG functionalization function. And notice that we'll only do this for CUDA, and we'll only use this if this is on. So if we look at this, remember this is happening at compile time. What is this doing? So for every single op, we're going to insert a new input into the forwards graph. In PyTorch, we call these inputs to the graphs placeholders. And so we call this forward RNG state and then some index. We will also add an input to the backwards graph. And here, we basically will replace the op that had the randomness with this higher order operator that will basically, under the hood, call the original operator. But critically, this hop will use this RNG state. And what that will allow us to do is in the backwards, we can use the same RNG state as we saw, basically in this example, to ensure that the recomputation is consistent, has consistent numerics between the forwards and the backwards. And now if we look at the runtime wrappers, we can see that at runtime, we basically will extend the inputs with basically a series of generators. And then critically, we will call this .manual seed on each generator with different seeds. And the reason we do this is so that the generators don't all generate the same values. And so we still have some notion of randomness. And then we also do the exact same thing. But notice that the seeds of I is going to be the same for both the forwards and the backwards. And then the last interesting thing about this is this idea that, typically in neural networks, you run forwards, backwards, forwards, backwards, forward, backwards. And that's great. But sometimes we might do forwards, 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 backwards. And when we run that first backwards, we don't want to use the RNG state of the last forward. We actually want to use the RNG state of the first forward. And so there's some bookkeeping here where in the saved backward tensor states, we map the iteration index to the RNG state. And what this allows us to do is basically when we call forwards, 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 backwards, we can say, oh, we're doing the first backwards, so let me look up the first forwards and get those RNG states and use those when we invoke our backwards. Yeah, and I think at a high level, that's basically all I wanted to cover. There's some other small things here and there, but hopefully this gives you a broad overview of activation checkpointing and random number generators. It took me some time to realize what was going on under the hood. So hopefully this was useful for you, and I'll see you in the next one.